Hello everyone, welcome to another devlog. So today we're going to be going over the entity system and we're going to design it all from the beginning and just take you through the thought process that we're approaching for this game. So on the screen here what you see is that there's really two different ways that you can approach entities in a way. You can kind of just group every single field that you possibly need into one entity structure and just have like an entity just has everything in there, so no matter what entity type it is, it can just do anything you want. Another kind of approach is this sort of archetype approach where you sort of like break your entities down into distinct types. They're hard-coded into different types, and you simply take the fields, you only put the fields in there that you need for that type. So the knight has basically all of them, right? And the chest is missing the weapon and armor slot, and the tree is missing the inventory as well. But in a real game, you're gonna have tons more fields and properties, and so really the mega entity structure can actually get quite big. And also you end up with tons of different types, and it could get maybe quite crazy trying to deal with all the different types as a hard-coded type in the type system, right, at compile time. So a nice thing about the approach with the sort of mega entity is you have one type and everything is that type. All functions that you make work with that type. You don't have to make different functions for every different type. And if you want to iterate over every entity with a particular field, say you're saying, hey, all of the entities that are around me right now, can I look at all of the health of those entities? And I want to obviously attack the one with the least health. If you do that with the archetype approach, you might have to make a function which iterates over all the different entity types, and then does specific logic there, so it can get quite fiddly there too. But obviously the thing that is improved over the archetype approach is you will use less memory, especially when this entity type this mega entity type just gets bigger and bigger and bigger because it's got to fit more fields. There'll be less wasted memory. And another thing you get with the archetype approach is that the fields are more tightly packed together versus the entity one, because entity one could just have every single field in. So you'll just have a bunch of like padding basically between the fields that are actually used and not used for this entity type. Whereas like for an archetype one, they're all tightly packed together. But I think it's kind of rare where you want to pick up an entity and see and read every single field from that entity for a particular task that's processing that entity right now. Typically you just want to say check the health, right? You don't want to check everything else about it usually. Okay, so if the game was just going to have 1,000 or so entities, I wouldn't necessarily bother trying to worry about this code so much. But the game that we're going to be making, I've estimated around 73,000 entities to be simulated, probably all within the same frame, maybe over a few frames. So I would like to just at least pay a little bit of attention to designing this thing more properly. So imagine, again, we have that scenario. We're trying to find all the knights in the area which have a certain health, that we can, pick the one with the least health to attack that one first. So what we're going to be doing is iterating over all of these knights. We'll read the health field, and then we'll also read the coordinate field and get like a distance from our character, and also get the health and work out basically like the one that's kind of closest but also with the least health. We'll go and attack that one first. So we're just using a couple of fields here. We're not bothering looking at their weapon or armor. For some reason the algorithm doesn't do that, but imagine it's just these two fields. So when you're going over this array of knights, you're only looking at these two fields, and the rest of them you are not looking at. So if you know anything about CPUs and CPU caches and the way they work, You'll be looking at this and you realize, hang on a minute, this is half a cache line. So it's 32 bytes. So you'll be able to, whenever you go over this array of knights and you start looking at this character here, you'll probably load this knight and the next one if this is aligned to a cache line, and then you would look at the next knight and you'll be able to read that one from cache super quick. So you pick up those fields in the next knight. But when you go to the knight afterwards, you would have to pull in another cache line from main memory, and then also, you know, just pick up those two fields, coordinate and health, and then operate on that data there. So essentially the rest of the fields are kind of wasted in this operation. We are scanning over these knights and polluting our cache on our CPU with a bunch of data that we don't actually need. So this is going to have an impact on performance when it comes to reading over a bunch of entities just to check if the health is low enough for us to attack. Right, so one thing to take note about the CPU is when it reads the knight 0 and 1 in the array, and it's already pulled in that cache line, it's probably going to predict that you're going to go and read the third and fourth knight. So it could preemptively go out and prefetch that cache line from main memory and pull that into the cache. But you're relying on that system to do it in time, because you might quickly operate on that knight data and you still have to wait for that memory to come back. And also, again, you're still wasting the cache with extra memory that you're simply not going to look at. So I've just done some quick Googling into how long do you have to wait if there is a cache miss. So if we try and read from a location in memory and it's not in cache, what is the penalty for that? So if it is in the L1 cache, which is the smallest cache but the fastest cache and it's closer to the CPU, typically it says here it's about 1 to 2 clock cycles. So that's just basically like the same as like an add operation. It's very, very quick if it's just there in cache. The L2 cache is much bigger, but also a bit further away. So this one takes a little bit longer as well. So this one will take 5 to 20 clock cycles roughly. Somewhere around these numbers they probably vary from hardware to hardware. And then if you miss, there's also an L3 cache, which is probably somewhere around the ballpark of 50 clock cycles or maybe a little bit more. And then if you miss all of those caches, you go to main memory, and these ones will end up probably being around like 200 clock cycles. And so that time can just be used for other things, like actually performing operations on the data you've already read in, right? So ideally, you want to try and keep stuff in the L1 and L2 caches. Right, so this structure and this type of data layout is known as an array of structures. So when you put your knights in an array, you have an array of struts, right? That's the way you think about it. So this one is typically quite poor when you want to operate on loads of data of the same field, because you've got to stride over all of the other fields to get to the same field in the other knight, for instance. Whereas this approach here is known as structure of arrays. So instead you have a single structure where each field is an array of all of the properties. So say if you have a knight at index 2, you would index into each of these arrays at slot 2. And that would be all the data for knight 2. So I've kept this whole mega entity concept and archetype concept, but now instead you have one single structure. We have arrays of properties, and this is every single property that could ever be in any entity. And you have so any entity can get any property just as simply as turning the bit on in the properties bit set. So if you have entity, say in slot 3, and you can read its bit set and know which slot 3 coordinates, health, mesh ID are going to be enabled for this type of entity. Whereas for the archetype approach, we just have arrays for all the properties that we're definitely going to be using for that archetype. And you could still add optional fields or optional properties for the knight and the chest and the tree, for instance. But that also comes with some downsides, which you'll see in a moment. Right, so with this approach, you might be thinking, great, everything's next to each other in memory, so now we should just be able to iterate over the fields that we only want to use, and we'll only be pulling in the data that we want to use, right? Well, not necessarily. So with this mega entity type, there's a problem where, say if not all entities have a health field, right? Because their properties bit set says you don't have a health component, if you will. So entities 0, 1, 3, 4, 5, 6, 7, 8 do not have health. So when you go and scan over and iterate these entities, you're looking for ones that have a health component, and you're only going to go and pick up one health component out of these 8 entities. Okay, so you might be thinking that now that we've got all of our properties in a nice array, just iterating over all of that whole array for the properties that we want is just going to pick up everything in cache, and it's going to be great. Well, there's still actually some more problems to solve, so we're just going to look at those now. So if you take a look at the entity pool, we've got a bit of an example here where, it has this bit set where not every entity needs to have every component. So really it's going to create holes in the data when you scan over the array. So here's an example. The coordinate is fully enabled, it's just there for every single entity here, from 0 to 8, whereas health is only around for entity number 2. So when we scan over the health stuff, we're going to be scanning over these guys, and these are not going to be entities with a coordinate and a health component. They're just going to be, ones without health, so then they're not going to apply to our algorithm, which is find the closest entity with the least health. But then finally we find one, and then we can run that logic, right? And so there's a bit of wastage by scanning over useless entities here. There's also more wastage where we haven't really got rid of that problem that we had before. We've just changed it out for another one. What we've gone and done is, instead of having useless fields that belong to the same entity, instead now we've got useless fields from other entities which don't have a health property. So we're still pulling in caches with useless data. So this is where having a pool per archetype solves this problem, right? Because you can guarantee that every single field is going to be used by every single entity inside this pool. So that's going to be really, really helpful. So when we scan over all of those entities, we know that all knights have health. So it's going to be very efficient in that way. But of course, you can also add that properties bit set to these archetypes, but the trade-off where maybe it's a very rarely used property, or maybe only 1 or 2 of them disable it, right? So yeah, it is a trade-off at the end of the day, but you really want to avoid it where possible. Right, so you might be thinking, now we're using archetypes, there's not going to be any holes in our array, in our property arrays, because every knight that's allocated is going to use all the properties, so they're guaranteed to be there, right? Well, since this is a knight pool, we're going to be pool allocating these elements, meaning that we can individually free and allocate each element in the array. And that's the allocation strategy we're going to be using, because it's nice and simple, and it's kind of fast as well. So because of that, it creates holes in the array. So if we say allocate all 8 of these slots in the knight pool, and then we deallocate 0, 1, 3, 4, 6, 7, what you've gone and done is created some holes. So how we get around this problem is we need to not be directly referencing the entity in the pool, the offset into the pool for this entity. We need to have a level of indirection here such that we can have an automatic defragging system that simply just reorders the pool such that the data is next to each other as possible. So we should be able to have a defrag system that runs at the end of the frame that will take element 2, 5, and 8 and squish them down, or just move them down to 0, 1, and 2 and update the references to them in some lookup table somewhere. So if you give someone direct access to where the entities are in the pool, doing a defrag system like this is going to be harder because you'll have to chase every reference throughout the whole code base and somehow update it or have a way of renewing it. Right, so now that we have some defragger in our system, we've basically solved the problem now where we can iterate over all the entities in the pool in a cache efficient way. But there's another problem. I'm going to be having 73,000 entities all across a bunch of different worlds. So obviously I don't want to iterate over every single entity. What I want is the entities that are near me in 3D space, or maybe on a 2D plane, but yeah, in 3D space. So what we actually need to do is organize the data in such a way that all of the entities that are nearby in 3D space are also nearby in physical memory. So you can imagine you got this game world, we're looking top down because our game is top down, and you can kind of break the world down into zones, or you can call them regions or maybe chunks. And the idea is, say we've got this guy here, he needs to be able to look at all of the entities, like iterate over all the entities that are nearby, which have the lowest health. So the approach that I've come up with is we actually need to have pools per chunk. And then we can iterate over those pools per chunk and check all of the entities within a close range. So you can imagine, like, if this is an AI here, and we're running the algorithm again where we're saying, find all the entities that are near me that are closest to me with the least health, and do some sort of work out which one takes priority to attack first. So imagine if the attack had a radius like this, or like the player has a radius like this, is very blind, doesn't have fast sight. You would simply just look up all of the entities within this region, all the different archetypes which have health and which have a coordinate property, and iterate over all of those. We'll iterate over this box, we'll iterate over this little person here, and this, I don't know what that is, a coin, I don't know. And we would find out that they're actually too far away, so we won't bother, looking for another, like, this search has failed, it hasn't found anything. Now let's extend our box. Our radius, or is maybe this like ellipsoid thing here for some reason, I don't know why, because we're looking this way and we've got supervision. So now the regions that we need to look in is this region and this region. So we look over all of our entities, this one, and this one, because these are the different archetype pools, and we discover that this one has a health component and a coordinate. So we, get the length of the vector and get the health, and we've got a score for this one. Now we iterate over all of the entities in here, and we find out that you know, this one has a health component and also a position, so we get the vector, get the length, and make a score for this guy. Now we've searched over all the entities, we can simply just go and attack this guy. So with this approach, it should heavily cut down on the amount of entities that we need to actually search. And when we're searching over entities, we should, as soon as we pick up one entity, if there is more than one entity, we should be able to hit, like those should already be loaded into cache, and we should be able to operate on that data more effectively. So there is a couple of things that I want to address, and that is that doing this archetype approach is obviously far more complicated than doing this mega entity approach and doing any form of like structure of arrays is far more complicated than just doing an array of structures thing, right? This is way easier to debug and implement these arrays of structures, but structure of arrays is more complicated, and furthermore, archetypes are also more complicated as well. So another thing to be aware about with the archetype approach, it is not a golden bullet. You have to be very careful with the fact that if you've broken down your archetypes into such distinct types, like a knight, chest, or a tree, these are probably terrible examples because you might not have lots of knights in your level. You might not have lots of chests in your level or lots of trees. So what you're going to do is you're going to, you know, only have, say, 3 slots in the knight pool and 3 slots in the chest pool and 3 slots in the tree pool, for instance. And as you iterate over all the healths, you've gone and pulled in one whole cache line and you iterate over 3 of them, and then you're done. But the health component is only 1 byte, so you can fit 64 in a single cache line, and you've just wasted most of that cache line with a bunch of empty slots. So you really have to be aware when you're designing your archetypes, when is it a good time to break it down into another type? Are you going to be having tons of knights? Are you going to be having tons of chests, right? Maybe you need to generalize the types better. So maybe, as an example, having a static object and a dynamic object entity type. And then maybe in the future, when you have tons of projectiles and you want that in the entity system, you can break that into a separate archetype with just the specific fields there. Right, so we still have downsides with this archetype approach that we just have to be aware about. And that is that now we've gone to this structure of arrays, that the debugging experience is going to be a lot harder. So if you just had a structure and a pointer to it, you literally just look it up and, you know, look at the field and print it out. But what we have instead is these big pools, and you have to have like get your entity index and index into it to get the value that you want. So doing this in a debugger will be a little bit harder, but if we also have printing that we can still do though. So the way we're going to tackle this archetype pool problem is we're actually just going to make a simple text file which lists all of the archetypes and all of the properties. And then we're going to have a little script which generates all of the code to do structure of array and array of structure archetypes, so we can compare speed and also make changes to the code generator and just add new fields to the text file and change the code without spending a lot of time doing it, right? Once the code generator system is in, we just operate on the list of entities and properties, and we should be able to change how the system works under the hood without too much of a pain. So let's talk about how we can do the allocation strategy for these archetype pools. So we're going to have one of each archetype pool per world, and each property is going to get its own allocation, right? Allocates one massive array to store all of the entities for the whole world. So we're going to fix allocate the chunks from here. So imagine this is at the chunk of the world at 0, 0, 0, and all of the entities are going to be stored in here. So this only has 3 entities, and this will be at 0, 0, 1, and this one will have maybe 2 entities, and then this one is at 0, 1, 0, for instance. And this will maybe have like 4 entities. So you'll notice that we are still going to have this sort of like spacing between these chunks, but we've max allocated how many night coordinates there can be within each chunk. And when we have to iterate over these, we can at least iterate over these contiguously, then jump to these ones, iterate over those contiguously, then jump to these and iterate over these contiguously. But that's only if we have operations that span these three areas. So there'll probably be a trade-off between like a chunk size and how big you want the chunk size to actually be, because the smaller it is, the more chunks you have to search and pre-allocates as more holes. But the larger the chunks are, the more entities you'll fit into a single area, but the more entities you'll have to search. So there'll be a nice trade-off there to make at some point. We also want to support some level of random access to an actual entity. And as I mentioned earlier, we have a sort of defrag process, so we don't want to have a direct reference to an entity within an archetype pool, because we want to allow the system to be able to defrag and move the entities around and keep them more contiguous. So we're going to have an entity ID. It's probably just going to be an index with a counter bit in there or something. So if we free it, we can keep track of reused IDs or something like this. But we're going to index into an entity record array and then pick up what is our chunk coordinate, our archetype, and our element index. So we should be able to know what archetype to look into, which element within the archetype array, and then also a chunk coordinate, so we can offset by the chunk and then offset by the element within the chunk. Another benefit of doing it this way is that you can have an entity ID to any entity and it's not specifically hard-coded to a specific archetype, which can be quite problematic when you use archetypes when you have pointers, because it's strict typing. But we probably also want to have strict entity IDs for different archetypes, because then maybe it could make the lookup a bit quicker, I don't know. Right, so another thing that we could do is actually just get references directly to objects, but because we have that defrag process that's going on, these only will be actually valid for the duration of a frame. So at the start of the frame, what we could do is use like entity ID or that night ID, fetch the entity record and generate a single offset into the night pool, and we'll call that night reference. And so if you're accessing the same night multiple times, it will mean that you can avoid doing multiple lookups into this entity record table before you go and look at that same night, basically. Right, that does it for this devlog, guys. Thank you so much for watching. If you want to catch the stream, it's day 150 on the VOD channel here. And then also there is a Twitch channel if you want to come and watch this live and come and hang out. There is also a Discord channel if you want to come and hang out off stream and outside of the YouTube channel comment area too. And yeah, if you want source code access to run this on your machine, if you support via Twitch or Ko-Fi, as a thank you, you get source code access to the game and engine to run on your local machine. Thank you so much for watching, guys, and bye-bye.